This thing is working. Today we're going to be doing more soil stress. Part 4, increase in stress. So we're going to actually be talking about what happens when we put something on the ground surface that is super heavy, like a building or something important that us geotechs are going to have to design. So how that changes the in situ stress and the increase of stress that we see resulting from that. So first of all, happy almost week end of school. We're getting there close. This is going to be a little different. Foundation solutions and problematic soils and stuff. These are probably going to have different titles. But yeah, we have this week, next week, and then it's finals week already. So just a heads up with that. The homework 4, it's already been posted. It's already been due. I will post the solutions after this. And then just a reminder that the only thing left really on the docket is the individual lab. So that should be posted now. You should be able to see the, it's in the lab section of our Canvas, since the Canvas is separated into 2, but it's an individual lab. You should have the instructions in there. I think there's also like an example report that I made. Pretty straightforward. There's also, if you look at the assignment, there's a rubric on there that like gives a little bit more detail of like what I'm actually going to be grading it for. So yeah, if there's any questions on that, and again, if you don't want to just choose a random location in Florida, let me know and I can send you just a random spot if you don't want to put any effort in that. So no worries for there. Any questions on where we are? Yes. Why is it an hour early? I don't know. That's literally just the UNF sets the final schedule because so they don't overlap with other classes. I wish. I don't know. I mean, years past, like I've asked everybody like what everyone's exam schedule is like. But usually there's always an exam like right after it because they try to squeeze all these finals in like a couple days. So unfortunately, yeah, 7 a.m. We're just gonna have to deal with it. I think we're gonna have to stick with it. Start waking up earlier, like 5 minutes each day, and you'll get there. So so yeah, I'm sorry guys. I'll bring in coffee that day. So mainly for me, you guys can bring in coffee.
Yeah.
Next semester?
Yeah.
Not my class. That is rough.
One is a Monday. Yeah, that's hydraulics, and it has a lab on site. Yeah.
Fridays, I thought you like weren't allowed to have engineering classes on Fridays. That's like the whole rule. Jeez. Would you guys prefer morning classes or like a 3 p.m. class?
Morning.
Yeah.
9:20 is
Not,
yeah.
yes. 8 is ridiculous.
Let's round up to an even 10. Yeah. Well, I don't know. I wish we had more of a say. I mean, I'd hate to be the person trying to organize all this stuff, like all these classes and making sure there's no overlap. But I definitely wish we professors would have a say, but every professor would be like, oh, 11 a.m. Like every person would want that slot. So yeah, exactly. All right. So what we're going to be covering, it's going to be in this textbook primarily. And then also what you'll also see is I uploaded a PDF of this other textbook that we haven't really been pulling from. So it's chapter 10 DOS textbook. It's a really popular geotechnical textbook. And I just kind of took some pages from that and uploaded it to Canvas because a lot of the things we're going to be covering are these crazy math equations that, of course, then engineers simplify into these tables to make our lives easier. So these tables are on the internet and they're like everywhere, but I just want to consolidate them at least for your, for you guys for that one. So you'll see right under the lecture notes in whatever this week module is, week 14 module, you'll see this other PDF. So go ahead and download that. And when you look through it, you'll see basically all the tables that I'm presenting in this lecture. So that's in that one. So last week and the week before, we were talking about in situ stresses. So in situ stresses, Let me write it right over here. So in situ, who could like tell me what the term in situ means? Like what like when you think in situ, what do you think of? As it is? Yeah, somebody else say something? In place, yeah, exactly. So this is like the natural stress conditions before humans come and change stuff, right? So like untouched, in place, natural, like as it is, like just before us humans come and build stuff or remove the ground or anything like that. So the in situ is always shown, usually when we're talking about stress, as a sigma. And then if we're talking about vertical, then we put a V there. And then we'll put a 0. Oftentimes it's like a 0 to show that this is the initial conditions. So there's no changes yet. This 0 is representing as like untouched, like initial from the start conditions. And what we've seen is that like if this is a homogeneous soil, which means the unit weight is consistent through the entire thing, at all depths, the unit weight is the same. Then this in situ stress will just increase vertically, like as a line. So this in situ vertical stress would just be the unit weight times the H, or whatever, at whatever depth we care about. So we also talked about like looking at these as like a soil layer. And so if we have different soil layers, then obviously we would have different gammas. And so this profile would have different slopes depending on what that gamma is. So it may not be a perfect straight like triangle, but what it would always be is a bunch of triangles like with different slopes added up to them. So what would happen then if we add a large soil fill or a surcharge or ponding or flooding? So what happens if, let's just say like we come in and we add a massive amount of soil here, an extra layer that is across the whole project site, or what we would just call like an infinite amount. And so this has a unit weight as something like this. If we call this like an infinite surcharge, like something that is super large, like you're going across the entire project, then what we do is we just treat this as another soil layer. So what this would do was would just simply shift the entire curve up like this. And we would just see something like this. So this would be the entire shift. So this would always be in the case if it is like a large soil fill, so the entire project site. If it's ponding, you know, like if we have like this is unit weight of water, something like that. But it would always be shown as just adding some stress here that's uniform. So most of the time though, when it comes to geotechnical engineering projects, we aren't going to be adding a massive amount of fill. We're not going to be changing an entire project site, adding up, you know, giant acres of soil. Instead, what we would be doing is adding just one like isolated object, right? Like a roadway, like a skinny roadway, or a building foundation, or a warehouse, or you know, even like a dam or something. These are going to be concentrated soil fills. These are going to be building foundations. These are going to be anything permanent or temporary at the soil surface that is not infinite. And again, it's not actually infinite, but generally like that's what we would model it as, like, you know, just consider like large project sites versus something that is actually measured, like a building foundation or something like that. So what we would see is that this isolated or concentrated object that is super heavy, that is adding stress, is not going to shift the in situ vertical stress uniformly like we saw before, but instead what it would have is some type of increase and then dissipation with depth. So this at or near the surface, what we would have is a normal amount of increase. So if this has, let's just say this has a weight. And let's just say this is across a surface area here. Or here, instead of W, let's just say this is F, like this applies a force. And it has a footprint. Then at the surface, we know that this stress is going to be the force divided by the cross-sectional area of that object. And this will be at or near the surface. So if you were hanging out right here, if you were like an ant pile or something right near the surface, then you would be feeling the entire stress of that object. Now, as we go deeper with depth, the soil actually distributes the load horizontally through a phenomenon called arching. And this actually dissipates the stress. So eventually, if you get to a certain depth, then you do not feel anything from that structure above you. The soil is exactly as it is on the in situ state, and the soil or the stresses from that super heavy object on the top is dissipated, and it matches the in situ horizontal stress. So as this increase in depth, as we increase in depth, then what we see is this stress will dissipate. So this is really important if we think about, a geotechnical and a design aspect. Like we are adding a structure or something on the ground surface. We need to see how much that stress is going to change due to this loading, and at what depth will we not feel the effects of this structure anymore. It's super important for settlement analysis and also the strength of existing structures. So again, think about it. We don't have like subways here in Florida or like underground, but we do have like underground utilities and important infrastructure that is below the surface. When we load something on top of it, we need to see how much stress we're actually applying to that object to make sure that it's not compromised, it doesn't bend, it doesn't break, it doesn't collapse in or something like that. So the important thing that we see here is if we have the initial in situ stress, this super heavy object is going to cause an increase in stress. And so what we say is this is a delta sigma, and then we usually just say it Z because it's with depth. It's a function of depth. So this then adds to our new vertical stress. So you see the sigma V now doesn't have a naught, it doesn't have a 0 in the subscript. This is saying that this is our new analysis, our new like stress that we care about, which is the initial stress plus this increase of stress. So what we actually see is that this increase of stress is right here. And we see that this increase of stress, this delta sigma Z, changes with depth. So it's a function of depth. So at the ground surface, our increase of stress is delta sigma Z, because that object is being, applying directly at the soil. We feel the entire stress due to that increase of object. But as we go down with depth, this delta sigma Z will change. So what we see that is delta sigma Z is a function. So this F is just saying it's a function of, so it's dependent on the depth and the loading geometry. So there's a lot of analysis in this week, or to this lecture and next lecture, we're going to be looking at the many techniques to determine that delta sigma Z at various depths, depending on different types of loading geometries. So that's basically what we're going to be doing. And this is, again, really important moving forward in geotechnical engineering design. Any structure that you're building, any like parking garage, any even planters or any type of temporary or permanent structure, we need to know how that's going to change the stress level from its in situ state. because in situ state, like thanks to nature and just the time it's been there, it's usually pretty stable, right? In situ conditions, this delta V naught is going to be at a stable state. But once we start changing that stress conditions, that's when we have settlement, that's when we have failure, that's when we have things that us civils and geotechs need to care about. So what we'll see is a lot of people started thinking of these ideas a long time ago. Boussinesq, I don't even know if that's actually how you pronounce his name. I think it's French maybe, but way back in 1883, he was starting to develop this idea that a stress can be dissipated through a elastic homogeneous medium given a certain equation. So he came up with this really simple equation here that if we have a point load, so this is a point, so this would be in terms of a force, which means it would be like pounds or kilonewtons or kip, something that is a point force, not a force divided by a cross-sectional area. But at any location horizontally and at any depth away from it, you can determine that delta sigma z, that increase in stress. And so this very simple math equation becomes even more simple like that, and then becomes even more simple like this. And this is all based off of an analytical approach. So this is assuming that it is elastic and homogeneous. This is called an analytical, which is just a fancy way of saying they used physics and math. Anytime you see these fun things with a bunch of pi equations and all that stuff, that's usually an analytical approach. So luckily, you know, he was a mathematician. He did all this crazy stuff and all these fun things, likes to think about numbers and stuff. And then you'll see this big trend, or if you haven't seen it already, engineers come and they're like, let's make it simpler so we can actually apply it to everyday things. And so it was then simplified into this equation. So our delta sigma z at any point is equal to the point load, the original point source load, divided by the depth that we care about squared. And then we multiply that by some influence factor. And this, so the P again is the surface point load. And again, the point load, meaning it's a force. So it's just a single point. It's pounds, it's kips, it's kilonewtons. It's not a stress. The Z is the depth we care about, or the depth in question. And then this I1 is going to be the influence factor. And this is where the tables come in. So instead of doing this whole thing out, which theoretically you could, you know, if you wanted to double check your answer, because it really isn't that, like, it just looks sketchy. It's just R radius and then Z the depth. But all of this is encompassed in a table, and this produces that I value. And so this is where you would look into your DOS textbook, find that I1 table, or here on your notes right here, this is those tables there. So it's a function of R divided by Z. So if you need to calculate the R, which is the radius. So let me just highlight that again right here. If we're given Cartesian coordinates, X and Y, so a point that is a X distance away from our source and then a Y distance away from our source, then we need to use the Pythagorean theorem there, A squared plus B squared equals then R squared, and we would find that R value. So that's really important here to distinguish. Because a lot of times when you're working, they would just give you the Cartesian coordinates, you know, like in latitude and longitude or something. So we'd have to make sure to solve for that R. But the depth is the same, you know, a certain depth below ground surface. So when we have that R and that Z, then you can either plug it into this fun equation, or you can just look and see the matching I value, the influence factor due to that. And once we have that, just making sure everything's in the correct units. The P would be, a force, and then our Z would be that depth of interest. And then you just plug it into this equation. So our delta sigma Z at any point that we care about is P divided by Z squared times I1. This is why engineering is so fun, because we get to use all this fun math and stuff, but it's already been simplified by people who were dead already, and they make our lives a lot easier. So that's what you'll see throughout all of this. Again, if you look at these values, this I value is directly proportional to the delta sigma Z, right? So since this is not, we're not dividing by I, we're multiplying by I. As we move further away, so as the R becomes higher than the Z, as we move further horizontally, then we see this I value go down, right? Which would make sense, because the further we get away from our point source, the less influence we see. So as I always like double check, as we get closer to P, this I value increases. So that's just, something like logical that you should always check when you're reading these tables. Like think about your point and look at the resulting I value, make sure that it makes sense, like compared to everything else. So if it was right here, directly under it, then what we see is, then we would have the highest influence factor. As we move further away, then that influence factor will go down. Again, this is point loads. Who can think of an application like physically when you might need a point load? Like designing a point load, like what type of structure or object might apply a point load? A column? Yeah, like it could be like a maybe not a structural column, but like a pole, like telephone pole or something, or like some of these drilled shafts. Sorry, let's move this. Drilled shafts, or even piles of foundations. But really, point loads, there's really not many of them. Because if you think about it, everything is going to be applied over some type of like foundation or footing or something. So like all these structures, even though you see these columns coming down, like the one out there, the column will go directly into a footing to distribute that point load across a cross-sectional area. So point loads aren't often used, but you may need them still. But usually when you're designing these, you're thinking like a rough estimate, because these piles and these drilled shafts and these poles, like telephone poles and everything, although they still look like a point, it's still physically distributed across a cross-sectional area. So let's look at another version, vertical line load. So now it's still a point, but now this point is being applied in and out of paper in a line. So like this is just a little cross section of it. And we can visualize this as it being applied in this Z direction, or I guess it should be Y direction, like in and out of that. So what we see is it's derived from the same theory. So it's still based on the theory of elasticity. I should say that. So but now instead of looking at one single point, it's just derived for a point per unit length. So this would be like a pound per foot of length, or a kilonewton per meter of length or something. So it looks like a point in this picture, but just again, visualize it coming out of the paper and into the paper. So there's this other dimension to it. what we see is we can move this around, and actually we can solve for another wonderful little influence line. So now instead of calling it an influence line, we basically just say like this X and Z here. This is a function for vertical. So this is for vertical. So if we have an X divided by Z, so the distance away from the object, this ratio, then we would then solve for the corresponding value here. And then, yeah, so this whole thing is then plugged in, and then we can find the delta sigma Z in that way. So based off of our unit load Q divided by Z, whatever this value is, then we would then solve for that delta sigma Z. Let's just look at this example here. So let's just say we have a Q, a lowercase q, which is a unit or force per unit length. So 5,000 pounds per foot. So you could picture this as like, like a line of telephone poles or a fence line or something like that that's going out of the screen. And we care about like some utility line or something that is 10 feet horizontally and then 40 feet down away from that object. So what would be the increase of stress at that point? So what we would do is we'd find that ratio of X divided by Z. So we would look at 10 divided by 40 is equal to 0.25. So 0.25 we see is right here. So we would interpolate between these two, and we would see that this delta sigma Z divided by Q divided by Z is equal to about 0.563. That's just linearly interpolated between those two, since it's 0.25 and that's halfway through. So once we have that, then we can solve for our delta sigma Z by rearranging this equation. So it's 0.563 times our Q divided by Z. Again, our Q is 5,000, and then our Z is 40. We'd make sure that the units are correct. So Q, I'm just going to put it up here for room. Q divided by Z. This would be 5,000 pounds per foot, and then divided by 40 feet. So this all checks out, but you would want to make sure that the units are correct. So then we would get feet divided by feet, or divided by feet, which is in the units of pounds per feet squared. So our delta sigma Z in this example would be about 39.6 pounds per feet squared. So again, think about that. That should make sense, right? Because our point load is 5,000 pounds per feet, but we're going pretty significantly away. We're going 10 feet off to the side and then 40 feet down. So if you had a value that was higher than 5,000 feet, then you know that you made a mistake somewhere along the lines, because the stress is always going to dissipate with depth and horizontally as well. So your number should always be less than your point load. So this is a vertical line load. These are used again sometimes in like fence lines and everything, but again, what these is still, so like sometimes fences or walls. But again, like point loads often aren't analyzed because it's always going to be a cross-sectional area that we're applying any type of foundation through. But if we can do vertical line loads, then we can also do horizontal line loads. This is really beneficial because we always will be designing something to withstand the weight or this vertical loading, but especially in Florida, like we have wind, we have waves crashing on walls, we have horizontal and lateral loading as well that we need to consider. So the horizontal line load, again, is basically the same thing. But so the same equation, but now it's X divided by Z. And we have the same setup here. So still what you do the same thing as the vertical, where you would find your x divided by z, and then you'd find the corresponding delta sigma z divided by q times z. And then you would solve for delta sigma z. Important thing though is make sure you're reading the right table. This table, 10.2, is for vertical loading. This one is for horizontal. So the values are going to be different since the equation here is going to be different. And again, this is like a Q per unit length horizontally. So the applications. So wind, cars, love bugs crashing into stuff, a bunch of different applications, but any type of lateral loading. So a good application of this is like when we start actually working, we'll see that all of these forces combined on a structure are going to be summarized into a load at a certain angle. So like oftentimes when we're doing the analysis, we have the lateral loading, we have the structure weight. It's simpler just to show like this resulting force in terms of a percentage on like the ground surface. This could also be, not all the time does wind hit a structure completely horizontally. You could be having like upwelling from the ocean, and then, or like, in areas where there's mountains, the wind is coming off of the mountain and it's coming at an angle. So sometimes we have to analyze this load, which is a combination of horizontal and vertical at this certain, degrees angle or something. So what we do if we have something like this, so I shouldn't say horizontal, so this is a combined line load. But what we would always do is we would then, if we have something like this, we would place it into the resultants. So thanks to trigonometry and that stuff we learned in high school, we can find the resulting vertical and we can find the resulting horizontal load, and then solve those two independently and then add them up to find that increase in stress. So this increase in stress that we care about at point A so this is our delta sigma z, say A. What this is a combination of two things. We have a combination of our delta sigma z in the vertical direction, and then plus our delta sigma v or z in our horizontal or lateral direction. So again, to do that, we would first find the resulting of each one. So using trigonometry, knowing that our vertical can be found by taking the cosine, all that fun SOHCAHTOA stuff. Did you guys all learn this in like preschool too? No, maybe not preschool. But yeah, SOHCAHTOA. That was like the saver on the AP exams. But what we see is we do resulting here. Always check your calculator to make sure that you're in degrees and not radians. But we would have something like this. So now we have the resulting vertical and horizontal, and then we can do the analysis just like for the previous examples. So first we would look, let's do our horizontal. What's going on here? Okay, what we would see here from this one, this is our vertical. So if you look up the ratio again of this would be our X and this would be our Z. So look up that ratio and we'd see that our delta sigma z in the vertical direction divided by our q over z from our table is about 0.098. So from that, then we would solve for our delta sigma z. This is equal to 0.098 times our vertical divided by our z, which is 4 feet down. So our delta sigma z in our vertical direction is about 23 pounds per square foot. So moving on to the horizontal. Same thing, but we would look at the other table. So do not read the horizontal table. Wait, same. We see that this value for our horizontal is 0.125. And that should make sense, right? Because if we think about it, the horizontal should have a higher influence since our force is being dissipated in that direction. So the vertical component, if we were to actually think like how far away this point is from it, is much further than the direction that our horizontal load is being applied to. So we should have a higher influence value, which means we should have a higher, well, not a higher, but we'd have a higher influence value in this case. So H, same as before, 0.125. Although our influence value is higher, our stress, our original horizontal stress is lower. So what we see is that this delta H is only 10.7 pounds per square foot. This means now we have both of these terms. So our total would be the addition of these, and we'd see that due to this point load that's at an angle, be 33.7 pounds per square foot. Again, this, since this is a sigma, it's a stress, it will always be in pounds per square foot or some type of stress. So kilonewtons per meter squared, something like that. It would never be an actual point load. So with all this math on point loads and everything, luckily the same technique, or as we were saying before, like oftentimes like point loads are okay to estimate, but when we're actually getting into the design of a structure, what we have is a load being distributed across a footprint, an area of something. So they took the same math, Business took the same math, and started looking at like just if we had a point load and then modeled this single point load as a bunch of point loads going left and right, so like an infinitesimal amount, then we could create an equation for a vertical strip load. So to do this, it's really simple. He just did a very simple algorithm and then a Taylor series and all this fun math stuff. And we get this beautiful equation. So again, us as engineers, they already did all this hard work for us. So we get to simplify this into a table. Yeah. Yeah. Problem. Okay, so again, like all of this crazy stuff was just placed into another table. But what we see is there's a little bit more of variables in this. Now we have obviously the delta sigma z and the q, which is like the q is going to be provided to us. But now it's based off of the width of our footing or whatever, and then the x and the z direction that we care about. So what this is though, this is a vertical strip load. So what we are imagining is this footing going in the whatever direction this is, I guess Y direction, like out of the paper for an infinite amount. So just imagine, again, this is like a cross section of this. So it's just a giant, super long like footing, and then we're just taking a single cross section, and that's what we're viewing here. So these tables are a little bit more comprehensive, I guess. I don't know if that's the right word, but there's like, again, like they're on the PDF that I sent you, so I don't expect you to like to sit there with a telescope and try to read all this stuff from your notes. But this is going to be table 10.4. So make sure that you are reading the correct table. This is the variation of our delta sigma z divided by q, so that load per unit area. And then what we do is this is with 2 times x divided by z, or b, sorry, and then 2z divided by b. So how we would actually read this, again, what all of these values are right here, these are values of delta sigma z and q. So what we would do is calculate 2x, so 2 times the horizontal distance divided by the footing width, and then you'd also find your 2z divided by the footing width. And then you'd read the table wherever it intersects. So let's say like you have this and this, then what you would do is read this down here, wherever it intersects here, that is your delta sigma z divided by q value. So there's multiple tables because you'll see this one goes from 0 to 1, and then this one is the same thing except 1 to 2. So this slide 13 and slide 12, same tables, just continuing on. So when you look at your PDF in your notes or whatever on Canvas page, these will be just like right next to each other, like, right, but I split them up for this. So again, same thing, the 2x divided by b and then 2z divided by b, find these two, and this is intersecting. This is for vertical strip load. So this is a little bit more realistic for like wall footings, or even some structures, some of these massive Amazon warehouses that might have really long wall footings that are significant in length divided, or then we can use this analysis to determine how the increase might change to like one side or the other. But again, like most projects that you'll see, or if you've already seen, most of these projects will be under uniformly loaded areas. So these will be shallow foundations that are finite in area. So they're not modeled as a strip that goes continuous or infinitely over to one side. They have a specific dimension, so we can actually calculate the cross-sectional area. So we can actually calculate the footing here, the area, and then the load that's being applied to each one. Know what this building is? I'm just making sure. Okay, cool. Just want to make sure it wasn't too old. So yeah, obviously everything has an area, and we can actually find it. And so we need an analysis that is better suited for this type of to find the delta sigma z, or the increase of stress due to whatever loading we have. So the most popular method, and this one, I believe, or it was on the PE. I'm assuming it's going to be on the FE too. This is the 2-to-1 method, and it's very, very simple. It's an empirical approach now, so it's not analytical. It's not based off of all this fun like pies and like physics and everything. All this is empirically is meaning that like they did a bunch of load tests and they found that on average the stress will distribute at a certain way with depth, and this way that the stress distributes with depth follows a 2-to-1 slope. So I'll go over what this actually means in a second. But the way to visualize this, obviously we know as the area will increase, the stress will decrease, right? Because of this force divided by area. So we know that one way is at the ground surface. If we need to distribute our load more, then we just increase the footprint of our foundation or something. So what this technique is saying that as we go deeper in depth, the hypothetical area that our stress is being distributed around is increasing at a slope of 2 to 1. So if this is the ground surface elevation here, we have our original footing size. This is just a cross section of it. That at a depth of Z that we care about, this hypothetical application or this hypothetical footing size has now increased in area. So the stress is being distributed with that. So this follows a 2 to 1 slope, which means for every 1 foot we go horizontally, or I should say for every 2 feet we go vertically, this footing dimension will increase 1 foot horizontally. So we can find this, since these are just straight lines, we can actually set up a math equation that simplifies this. And so we can say that the delta sigma Z, the increase in depth at any depth, or the increase in stress at any depth Z, is equal to Q times B times L divided by B plus the depth Z times L plus the depth Z. And so this is where our original footing, so footing at the ground surface elevation, GSE, so the ground surface, has the dimensions B times L. So if it's a square, then B is equal to L, that kind of thing. So this Q times B times L, Q is the stress. So Q is at the surface. So this is the same as like saying sigma at Z equals 0. That's what our Q is equal to. So what we could also say is that this is equal to Q times our structural load times the area, which is B times L. So P is in like pounds or something, right? And then B times L, that would be like feet squared or something like that. So this equation is actually equal to P divided by B plus Z divided by L plus Z. Does everyone see that? How this right here is equal to P. And this is all because of this equation here. Because if we multiply Q times B times L, we move this over, then we have P is equal to this. So it's a very basic equation. It's not based off of all this like fun, like philosophical math and everything. Again, it's an empirical approach, which means it's based off of experimental data, but it seems to at least fit with good certainty enough that it's easy to calculate and still gives us a good result of everything. But let's look at an example of this real quick. So let's say we have a structural loading, a point load of 1,200 kilonewtons. So this could be like a structural load coming off of a column or something. Our structural engineer calls us up and he's like, hey, it's going to be 1,200 kilonewtons. And we're like, gotcha. So area of footing that we designed to distribute this footing or this point load across is 3 by 4 rectangles. So it has an area of 12 square meters, 3 times 4. Let's visualize. So at the surface, then it would look something like this. This is, again, is just the cross section here. And we know that with depth, this area is going to increase. And so that stress is going to be distributed over a larger area. So let's say, what if we need to define what the increase of stress is at Z equals 4 meters? So for this, what we would do is, again, the equation here is our delta, go back to red, our delta sigma Z, so our increase of stress is equal to our Q naught times BL divided by B plus Z times L plus Z. Luckily though, this whole thing here is also equal to, simplified as P times B plus C times L plus Z. So since we're given P, then we might as well use the equation with P. So what we see here is delta sigma Z, we'll just say is at 4 meters, is equal to the surface load divided by the area, the hypothetical area at Z equals 4 meters. That's basically what this equation is telling us. So the P doesn't change, that we're still taking that surface load, but now we're just dividing it by a larger cross-sectional area. So this area, so the denominator here at Z equals 4, this is equal to B plus Z times L plus Z, which is equal to 3 plus 4 times 4 plus 4, which is equal to 56 square meters. So at the ground surface, we have 12 meters cross-sectional area, but now using the 2-to-1 method, we're assuming that at a depth of Z equals 4, this cross-sectional area that our load is being distributed across is 56 meters. So it should always be greater because as we go in depth, we're increasing that cross-sectional area. So this means that our delta sigma Z at 4 meters, what we actually care about, is our original surface load, so 1,200 kilonewtons divided by 56 meters squared. So this is kilonewtons per square meter, which is a kilopascal, so it's 21.42 kilopascal, kPa. So again, like this equation, I will give you this equation on the test and everything, but still you should at least be able to recognize like what it's telling you, especially in the PE and the FE. This is something that you should be able to recall quickly and just do, like an easy math equation, because this here too is also only for a rectangular load, right? Like this is only for squares and rectangular, but this whole type of analysis where we have is equal to P again, P plus Z divided by L plus Z. This technically could be for any area, right? We just need to determine how that area is increasing with depth. So although this equation is set up for a rectangle or a square, circles would technically have the same thing. We would just have an increase in radius or increase of diameter with depth. I mean, anything else, like you could do trapezoid or something, it's a little bit more difficult, but yeah. L, yes, yeah, so this is a rectangular footing that technically has this L here. Yeah, so it's in the Y direction or whatever direction that is. So the technique, it's very simple to analyze, and it provides a good estimate. This would be one of those things where you would need to use your engineering judgment in the real world. If you were designing a nuclear reactor or something really, really important, you should probably do a little bit more analysis than just use the 2-to-1 method. If you're designing a Wawa over sand or something like a Holiday Inn, nothing against Holiday Inns, but something where it's like a little bit more controlled and a little less critical, then this might be an okay method. And this is a P, this isn't a D. So what this actually does is this only calculates the average increase in stress. So only at a depth in question. So this is saying like, okay, the stress right here is equal to the stress right here. It's all averaged, which like think about like it like physically. Do you think the stress in the center of our structure is going to be higher or lower than the stress on the outside beyond the scope of the structure? Should probably be higher, right? So what this method does and what it's limited to, it only provides the average. So even though the actual stress might look something like this, what this technique is doing is only providing the average value. So something like this. Average value. Obviously, if we are wanting to find the increase, like if we have a specific utility line or a tunnel or something at a certain location, then maybe this technique isn't going to be the good technique to use. So sometimes we need a more accurate technique to pinpoint certain locations. So this is, especially for underground structures and that kind of thing. This is really important. So 2-to-1 method is still used. It's used in a technique that we're called consolidation, which is where we look at like settlement of clays due to a loading, like so squeezing of clays over time, which we'll unfortunately just talk about more in the part 2 of this class, the foundation and design of analysis in fall. So that's why it's my plug for that class. But 2-to-1 method is used for like that in primarily, but if we're actually looking at analyzing structures, we need a different technique, which is what we're going to talk about next class. So these more robust techniques, same kind of format, finding the point increase due to different foundations, and we'll talk about that. So see you guys on